from us. That's me. I'm Molly. Hello. That's Ro. And you use online. Hi, you. And we've been putting together PMW for you over the last couple of months. So, what are we going to do and how are we going to do it? To begin with, in this first session, I'm gonna keep this opening really short, but just welcome you. And then we're gonna play bingo, because there's nothing that says Monday morning like playing bingo. But the goal is just going to be to make sure that we introduce each other and say hello and learn a little bit about us. Then we'll have a talk from Nate Foster, which I'm really looking forward to. Coffee break. And then the end of the morning is going to be a talk from Magnus Madsen, and then our PhD panel from current PhD students. Then there's a big lunch, for which I would encourage you to use the things you have learned this morning and talk to each other or talk to other people, right? Introduce yourself to some senior folk. After lunch, we'll have our fabulous career panel, where you'll get to hear about what post-PhD careers look like. And then there'll be another coffee break. We like to be caffeinated, apparently. And then at the end of the day, we'll do a little bit of wrap-up, and then our small group mentoring sessions, where a bunch of folks that you haven't met today will come in and be able to answer your specific questions or really talk about what it's like to do graduate work in programming languages. Important fact. There are a lot of QR codes that I flew across the Atlantic Ocean in on the seats. And so please, especially if you received funding, I love it, the phones. Please do fill out the attendance form at the beginning of each session. That is really helpful, especially given the expectation that you attend if you received travel funding. If you didn't receive travel funding, but you're still here, feel free to let us know. This is useful for us to keep track of statistics. And so this is available throughout the day.
No, I'm one of those people.
Great. I'm going to turn it over to our actual local Portuguese folk to give you a little welcome.
Hello. So there are 2 slides about Cascais. I have to say first that I'm not from Cascais. I'm not even from this part of the country. Okay, so when I'm here, I'm a tourist like yourself, or most of you. There are actually local Portuguese participants who are from the area and could provide more value than what I'm about to say. And there's also Google with loads of touristic information. So Cascais is a very nice place. It's one of the most famous touristic resorts in Portugal. The weather is usually not like this, so you were a bit unlucky. Okay, so I looked at photos from last year, and it was very sunny and very warm. So this year it's going to be very wet. But nevertheless, there are many nice things to do. So what is Cascais known for? The beaches, the seafood restaurants. If you like fish and seafood, this is a great place for you to be. And it's actually, if you like architecture, it's a very nice place because it has loads of old palaces and very nice houses that you can just look at and take pictures. It became famous because, that's the second point there, it was the first place of bathing. That will be the rough translation of the royal family. Okay, so at some point in our history, the royal family decided this is the place where we spend our summers and we go to the sea. And that brought a lot of the rich and the aristocrat people to Cascais, and that's why you have all the nice palaces. And of course, that created this charisma about Cascais, and many members of royalty have lived here. And something that is not widely known, to be honest, I don't even know if it is true, but it's written on the internet, so it must be, right? So there's a place that belongs to Cascais. It's in Estoril, is part of Cascais. It's called the Casino Estoril, so it's a casino. And it actually inspired Ian Fleming's first James Bond novel. And I think if you visit it, there are some photos there. I think they even recorded some of the films there. Okay, slide change. Okay, so what can we do nearby? So, I mean, these are just some recommendations. What we really suggest is that you just use the internet, okay? So Cascais, Lisbon, it's the most, perhaps, the most touristic place in Portugal, maybe compared to Algarve, which is in the south. And there are many nice things to do. What I like to do, for example, is just walking through the streets in the historic center. You'll see the traditional pavements. You'll see the, many Portuguese things there. If you like museums, and I've put the museums here because the weather might be quite bad and rainy, there's actually something called the Museum Quarter. And you can, I don't know if you can buy a ticket for all of them, but you can ask in one of them if you can, okay? And they are all at an easily walkable distance from each other. There's a website there that you can visit. And there's a nice one if you like painting. So there's a famous museum in Portugal, which is the History House of Paulo Rego. So Paulo Rego was one of our most famous painters. And it's usually a big attraction here in Cascais. If you like nature and sea, there's the Mouth of Hell. What you see it in the photo there. So it's actually a nice walk there. And then you have these very nice views. If it rains, it becomes even more dramatic, I suppose, because the sea might be a bit more rough. It's a very nice place. The slides, which I suppose will be available, have a link with other recommendations, okay? And then outside Cascais, well, there are the two iconic places and touristic places that you can visit. So Sintra, it's roughly 17 kilometers away. There are buses. I think you can take, I think you have to take the bus or the train. And also Lisbon, okay? Lisbon is very well connected. I know that some people are even staying in Lisbon and commuting to Cascais. And there's a lot to do in Lisbon, okay? So there are not enough slides here to talk about Lisbon. So I suggest that if you can, and you have time, try to visit those two places. They are very nice.
Awesome. I'm going to do a quick fire round of tips for attending. So for a lot of folks, this is your first conference. If you go up to someone and you say, hey, this is my first conference, they're going to be super excited about that. And that also might be some trepidation, right? How do you attend your first conference? I think asking questions and not making comments is a great way to engage with talks and engage with information. Feel free to introduce yourself before asking your question, right? That gives some context, right? Like, hey, I'm Molly. I'm a third-year undergraduate. I have this question. There are kind of two ways of asking questions for most of the talks, not in PLMW exactly, but for all of the other SPLASH events. So you can raise your hand and speak into the microphone, as I failed to do at the beginning. Or there's also a text channel on Discord for almost all the events. Go to talks. It's really interesting, right? State-of-the-art research. One of the things I love about SPLASH is how many different venues there are, right? Tomorrow, there's like a huge list of things that you can do. And so prioritize the things that you're excited about. Keynotes are always a great example of talks that are built for a broader audience and from really interesting people doing really interesting things. At the same time, don't go to talks, right? Talk to people, talk to other students, talk to other researchers, and really get a sense of the community. It's really broad and vast at SPLASH, and so think about both of those things, right? A lot of people I admire have told me in rooms like this, it's not just about going to the talks. You can read the paper later. Being in the room with the people is a really great experience. For those who are attending virtually, there'll be during the icebreaker, which is going to happen in just a couple minutes, there'll be a quick video chat with you, so please do join there. The rest of SPLASH looks like this. We're on Monday, and then Tuesday through Friday, there are many, many events. I do not know what all these acronyms stand for. The good news is that you can search them on the website. The single most powerful user feature of the SPLASH website is the search feature, where you can search people's names and talk titles and find them. But it's not super commonly used. Okay. I want to remind us that everybody here, right, should be adhering to the Code of Conduct and also PLMW values prior to participating to SPLASH and PLMW. This is really important because this space is about making, PL a welcoming environment. And so make sure that when you're interacting with people, you're following these. If you have questions about them, please let me know. Tips for attending PLMW in particular, right? Everybody here is early career researcher, right? But that has many different definitions. So one of the things I love to say to my students in their classes is, everyone has something to teach, everyone has something to learn. So don't go into that conversation being like, I'm going to show everything that I know, right? Go with curiosity and trying to learn. For funded participants, there's a dinner this evening at 7 p.m. It's going to be a fun mix of you all and our speakers and our panelists and mentors as well. So please do meet in the lobby at 6:15. And if for some reason you can't meet us there and you want to meet us at the venue, please ask me or Joao, and we're happy to give you the location. Great, we're done listening to me now. What we're going to do next is for you to meet each other and then the other folks that are in the room. We're going to play human bingo. What is human bingo? We have some bingo cards that have specific facts on them that we have created. So most folks in the room probably will sign their name on at least one square. And your goal is going to be going around introducing yourself to others and trying to see if they match any of the items on your bingo card. To get bingo, you get a row or a column, I guess a diagonal as well. In this bingo, we all win because we are meeting each other, right? And we're having conversations. So there is no particular prize other than if you show me your bingo card and be like, I got bingo, I will go yay for you. And that will be a prize. Okay, great. So there's a bunch of pens up here. You're going to want to just get initials on your bingo card, and Joao has the bingo cards to pass out, I believe. Awesome. So this is the point where we stand up and we mingle. Yes. Oh, sure.
And then it's the number. There are 30 of them.
Yes, just pass them out at will. I'm happy to take half a pile.
Okay.
I imagine people
And is
need
it
this.
All right, folks. That was great. Raise your hand if you got bingo. Yay. Raise your hand if you learned something new about a person in the room. Huzzah, we did our goal. Okay, great. So to wrap up this first session, it's my great pleasure to introduce Professor Nate Foster, who is a professor at Cornell University, who does research at the intersection of PL and networking and every single thing that entails in between. Nate is a great mentor and the co-organizer of the third ever PLMW. And so if you want to know about PLMWs of past, please ask Nate. Two other of my favorite fun facts about Nate. Nate is the most dedicated bike rider I personally have the pleasure of knowing, and also is maybe the only full professor I know who still has his undergraduate institution listed in his biography. He is a very, very proud Williams College alum. So with that, I'll turn it over to Nate. Thanks, Nate.
Great. It's really fun to be at PLMW. Really been fun to see how PLMW has grown and become such an institution over the years and how important it is for people who are new to the field. So I want to tell you about kind of some work I've done, but more like the philosophy behind why I chose to work in this area. And so I went back to my embarrassing PhD application essay. Please don't read it. But back in a long time ago, when I got into PL research, I was very into things like fancy type systems and really complex semantics. Having the right mathematical tools to model the most complicated things that arise in programming, and also mathematical foundations. I was really into foundations of set theory and even some philosophy. And so when I wrote this statement, I thought my career would be kind of going up into the ivory tower and working on these things. And so what I've done for the last 6 years has been to work on a language and programs that look like this. I won't explain this for you now, but let me just tell you, this language is not Turing complete. It's got a really simple type system, and it basically has no foundations, has no semantics, and it's designed by industrial practitioners. So very different from what I thought I would start out doing. So why? Well, sorry, animations are one off from the projector here. So why have I chosen to work in domain-specific languages? Well, one is, if you like thinking about language design, and I think for me this is one of the things that's really wonderful about programming languages, is that we get to design abstractions and sort of a universe in which we express programs, which may be very different from how they ultimately execute. And so if you want to do that kind of intellectual work, domain-specific languages are a great place for doing that. There are many, many different domains. There are lots of little challenges, and you can really kind of work your language design muscles playing in DSLs. That's not to say you can't do it in general purpose languages, but it's a little bit less easy. You have to deal with decades or even more of tradition. You have to sort of handle lots of extra complexity. So DSLs kind of give you these little areas that you can do language design in. The other reason is, if you think about the role of programming languages in computer science, there are lots of other people in other fields who are using programming languages, and a lot of them, of course, use mainstream, Turing complete languages. But increasingly, we see these little languages that are really important, whether it's for in systems or security or machine learning. There's lots of little languages that arise, and so if you want to influence the kinds of languages that people are using, focusing on these DSLs can have a really quick path to having impact on a field. Although I was kind of poking fun at the language I've been working on for being simple, not Turing complete, simple type systems and so on, there actually are a bunch of really hard technical problems, and so you won't be lacking for cool problems to solve. And I also think that DSLs are kind of a great lab for extracting general insights. So my great hope for all the work I've done is that I can sort of zero in on some domain, do something beautiful, and that will have value for maybe the practitioners in that field, but also some of the insights that we found from kind of zeroing in on this domain might then kind of escape that domain and feed back into sort of general PL theory. So I want to give you a little taste of this, highlighting one piece of work, but let me kind of take you through some misconceptions. These are not quotes, but they kind of reflect attitudes I've heard over the years, kind of, why do you work on these weird DSLs? So one attitude is, DSLs are somehow impoverished. They're kind of just, restricted subsets of like real languages like Rust or OCaml or Scala. And again, as I already argued, designing a DSL is not just about kind of picking syntax that looks nice and kind of throwing out features. I believe that good design always requires thinking about semantics, thinking about what are the sort of inherent properties of the domain that you're trying to model, what mathematical properties do the constructs in that domain have? Are they closed under composition? Do they support iteration? Do they support conditionals? All the standard questions you could ask about a general purpose language you can ask in that domain. And so I actually find that working on DSLs gives me a lot of chances to think about really hard semantic problems, even if you're working with something that's sort of, from a point of view of expressiveness, restricted. Another attitude I've gotten is sort of shifting from sort of the language itself to things like type systems and verification. Do these things have trivial type systems? Is there no interest in verification? Well, actually, my experience has been practitioners are demanding very rich types because these quirky little domains often have conditions or properties that need to hold. And they've sort of seen what's happened in general purpose languages with type systems and the rise of verification, and they're basically demanding the same things there too. When I first got involved with this networking language that I'll tell you about, I was talking to someone who's sort of a vice president at a big tech company, and he actually said, I've heard about this CompCert thing. For those of you who don't know, CompCert's a verified C compiler implemented in Coq. And he was asking, we really care about the assurance of the code that we run in our networks. Could we build a CompCert for this language? So kind of the word's out that the sort of golden age of verification and rich type systems, that it's possible to build very practical but also ergonomic and nice to use formal methods tools, and so they want those for DSLs as well. And then another attitude that I sometimes get from friends and others in the community is, okay, DSLs are like this niche, but the action is really in mainstream languages. And I think that this is wrong. I think that for lots of reasons, DSLs are actually where practitioners are interacting with programming languages, and this trend is only going to grow. So if you haven't seen John Hennessy and Dave Patterson's Turing Award speech from a few years ago, so you probably have some of you have probably used their textbook. They wrote sort of the famous textbook in computer architecture. And they argue why domain-specific architectures programmed through domain-specific languages are likely to be a really big trend in the future of computing. And they're motivated mostly by hardware reasons, but I think it's also true that sort of our software abstractions are about to get more heterogeneous. Okay, so that's a little bit of sort of high-level philosophy for why DSLs are cool. And what I want to do today is take you through one particular DSL that my collaborators and I developed a few years ago, a system called Leapfrog, and kind of take you through a little bit of what it's like to design a DSL and use it to ultimately build a verification tool. Let me first acknowledge the people who really did this work. So I don't think either of them are here, but Ryan Dunges was a PhD student in my group. He just finished and started a postdoc at Northeastern. Ryan's a really brilliant PL researcher. He has a background in math, but kind of got interested in building verified systems, and that's what he did during his PhD. And then Tobias Kappe was a postdoc in my group. He's now a Marie Curie Fellow at ILC in Amsterdam and also a professor at OpenU. So this is our paper. And I know that people here are coming from sort of a range of backgrounds and levels of maturity in programming languages. So I hope that there's something in here for everyone, even if you're new to programming language research. The core technical ideas here are based on things that I hope you've seen before. So in particular, we're going to make really heavy use of finite automata, just like you will have learned in an undergrad, maybe theory of computation or discrete structures course. There's going to be some semantics and static analysis. And if you have not done semantics or static analysis, I'll try to take you through kind of how what tools we're using and how we're applying it to this domain. And then this particular paper, we went all the way to building a Coq tactic that could verify network programs. And I won't go into the details of that, but I'll give you a little demo and kind of tell you how we organized that implementation. Okay, and it goes without saying, if you have any questions, I'm very happy to stall in the middle and explain if something's not clear. So please interrupt me. Okay, so the DSL I want to focus on for most of the rest of the talk is a language called P4. And confusingly, P4 is actually 3 languages. Maybe they should have called it P3. But it's really kind of 3 other DSLs that are kind of glued together to give you the full language. Ryan likes to say it's like that cartoon of a bunch of dogs in a trench coat kind of masquerading around doing stuff. The most interesting parts of the language are it has a sublanguage for describing how you parse network packets. And the yellow box there kind of shows a little snippet of code. We'll explain it in detail, so don't need to read it now. But essentially, this is the first thing that happens when you run one of these programs. You're in a network, you're a router or you're an operating system, and some bits arrive. And so before you do anything with those bits, you need to decide what they mean, and that's the job of the parser. The other piece of the language that's most interesting is there's these pipelines of what are called tables or match action tables. And these are sort of the main building blocks of how packets get processed, again, by a router or an operating system or any other kind of network device. I'm not going to talk about this today at all, but just to give you a sense of why this language is interesting, these pipelines are designed to map easily to hardware. So that's really the sort of main constraint that's guiding the design of this DSL is, you want to provide this abstraction that programmers can customize to suit their needs, but also let a compiler generate very efficient, both in terms of speed, but also in terms of the resources it uses, low-level programs. The other thing that's kind of interesting about this language is these pipelines are runtime configurable. So if you've seen any work on dynamic software updating or sort of self-modifying code, there's an aspect of this here where you're not just writing one program, you're writing sort of a family of programs that then another component will specialize at runtime. So there's some interesting PL challenges that arise in thinking about those kinds of systems as well. But today we're going to focus on the parsing. Okay, and just to give you kind of the big picture before we dive into the details, what this DSL is about is you take some network device. Here I've sort of depicted it as a network card. This is the kind of thing that you have in any server, or probably your laptop has one too. This has specialized hardware to process packets very efficiently. Increasingly, the hardware is programmable. So you can not just implement standard protocols like you'd find on a router from 10 years ago, but you can actually customize it to do special stuff. And people are still exploring, what should we put on these hardware? So, for example, you might take some piece of what's normally considered like application logic, like maybe the serialization and deserialization logic for some distributed systems framework. You could offload that onto the network card, and that might be faster, and it might also give you sort of different security guarantees than implementing it in software. That's just a taste of what people are doing. Okay, so just to give you again the kind of end-to-end picture, there's going to be a packet, which I'll draw as this little envelope with wings. It's just a bunch of bits. And so the first thing we do, we'll parse it. And this turns it into some kind of typed, structured representation, drawn here as a little sort of structured memory blob. Then we transform this, and typically this would involve, deciding how and whether to forward the packet, or maybe we would modify some of the headers, or indeed some of the data in the packet. And then when we're done, we have to transform it back into a binary representation, and then it goes on its way. So pretty simple, but also super important because it kind of sits down at the lowest layers of all of our systems, sort of moving data around and transforming it on its way. Okay, and just to motivate the work we did in Leapfrog, one thing that's really important about this language is that it's designed to map to high-speed network hardware. So the kinds of optimizations that a compiler always does are really not optional here. You can write programs, without thinking too hard about how they're going to execute on the hardware, but it's really imperative that the compiler be able to transform and normalize and streamline these programs so that they can actually run in the most natural way on hardware. And this includes both sort of traditional performance requirements like throughput. This is a, by now, sort of quite old quote, but it has some interesting math. So if you think about a 10 years ago network device like a switch, This is the kind of device that would be, maybe in your academic department in every closet on every floor connecting all of your computers. If it has 64 ports that each run at 10 gigabits per second, it needs to parse 1 billion packets per second, which is a lot. That's more than you could do on even a very fast CPU. There's also some hardware resource limits. So these kinds of devices, they don't have a memory with many gigabytes of data that you can just malloc or free. They have fixed amounts of storage. And so as you're mapping down this high-level programming model down to these devices, there's nothing like, if you've taken a compiler class, spilling a register into memory. You have a fixed amount of storage and that's it. So for these reasons, it's important that the compiler really be able to optimize programs so that they run well on the underlying hardware. The other little piece of motivation I want to give you for this domain is parsing really matters for security. This is a kind of hilarious fake protest from a guy at Dartmouth. But essentially, if you have some protocol that's running in a network and you have a whole bunch of devices that are parsing, transforming, and deparsing messages according to that protocol, and somewhere on the way, someone produces a wrong or somehow bogus message, that can cause big problems. It can, of course, lead to things like buffer overruns. It can corrupt state. And I don't have time to go into lots of fun horror stories, but I have them. So if you want to talk to me during the coffee break, really trivial things like a couple of bits flipping in a packet on a network device have led to things like databases being corrupted at large tech companies, like some of the social media sites have this happen. So it's really important that the sort of format or the type of the data that's flowing through your network be parsed the same way or correctly on all devices. So the problem that I want to tell you about is, which applies both to compilation but also to security, is how could we verify that two programs that implement one of these parsers are the same? And so this might be useful both if you're verifying maybe a pass done in a compiler, or if you're taking the parsers for two different devices and checking that they somehow agree. You need this way to decide this equivalence. Right here. Okay, so let me show you a little example to kind of motivate how, where equivalence might rise. And I'm going to use, as an example, a protocol that you probably never heard of. It's called, sorry, I have the labels wrong here. It's MPLS, multi-protocol label switching. I inverted the name. And just to show you kind of pictorially what this is going to do is, so I've got a packet. It's got a bunch of bits that I've written here in hex. And when I parse it, I want to parse it into a list of these MPLS records. So MPLS is a protocol that has list structure. And we'll say how this happens in the next slide. And then there's going to be some other data. There's some encapsulated protocol inside. Here I've just chosen it to be UDP, which is a common protocol on the internet. Okay, so our goal is just to parse this into this. And just to preview what's going on here, MPLS has this list structure. And whenever you have a list, you have to decide how to encode the list in bits. And this particular protocol chooses a really funny way to do it, which is the 23rd bit says basically, am I done or is there more? So because this is 0, we keep going, and because this is 1, we stop. Okay, the details are not important. This is the kind of thing that standards bodies argue over, but for this protocol, that's how it's going to work. Okay, so here's a little program we could write to do this parsing. And I'm going to start out by writing the program just pictorially, very much like finite automata, which I hope you've all seen in a theory of computation course. I'll try to explain it as I go. So this thing has a start state, which I've labeled Q1. Here's the state. And in the body of the state, it's got some stuff that happens. So it's got a little program that runs. And in this case, the program runs this extract primitive, which is going to grab bits out of the packet and put them into some typed representation. In this case, it's going to populate some structure called MPLS, and it's going to grab 32 bits. And then it has transitions indicated by these arrows. So if the 23rd bit is 0, then we loop back and do it again. And if it's 1, then we go to this other state where we extract UDP. And after we've done that, we succeed and go to the green accepting state. Okay, so let's see how this program would execute. So, hopefully this is all very intuitive, but just to kind of animate it for you. So the first thing we do is we're in this start state. We extract these 32 bits, and so we populate an MPLS record, as you see. And now we look at this. We have two possible transitions, but they're guarded by these conditions. Is the 23rd bit 0 or 1? And in this case, it's 0. So we're going to loop back and do it again. Now we parse the second chunk of data, which gives us another MPLS header. Now we do the same test again, but now the 23rd bit is 1. So now instead of looping back, we're going to jump down to the second state, Q2. We extract UDP. We have just enough bits to do that, and then we accept this packet. Okay, so nothing too complicated going on here, but a slight generalization of the kinds of finite state machines or finite automata you've probably seen before. Okay, so on the left is the program we just saw. On the right is the program that the compiler for this P4 DSL might, and it actually has a pass that would do this transformation. So the right is sort of an optimized program that the compiler could produce. And the idea in this right-hand program is the program on the left kind of parses too slowly. It does one record at a time, and it's only parsing 32 bits. And way down in the hardware, there's some sort of amount of data that you can sort of grab in each cycle. And if you parse too slowly, in the limit, if we parsed like 1 bit at a time, we would have a very slow parser. And in fact, this would affect the performance of our network card or router because we'd just be parsing way too slowly. So what the parser does is it basically unrolls and tries to produce sort of states that parse more data. And so in this case, it's not too hard to do. We can see that there's a sort of trivial self loop here, and we exit when the 23rd bit is 1. So the parser can basically run 2 copies of that first state in this Q3 state for this second parser. So it's going to extract 32 bits. It will store that, let's call that old. It's going to extract 32 more bits and put that into new. And then if they're both 0, we're going to loop back because there's more to come. If old is 0 and new is 1, we kind of got lucky. Like we had an even number of 2 MPLS tags, and we parsed them pair by pair, and then we ended just at the right border where we should transition and do UDP. So this is kind of the easy case. There's also a less easy case where old, the first record that we parsed, is 1. And so now new contains not the MPLS data, but the UDP data. It contains the first 32 bits of UDP data. So we go to this state where we kind of have to fix things up. And so we extract into some temp header 32 more bits, and then we assign UDP to be the concatenation of new, which was our mistakenly parsed MPLS header, and temp. So in either path, we'll end up getting, whether or not there's an even or odd number of MPLS headers, we'll get the right stuff, we'll put it into the right variables, and we'll end up in this accept state. Okay, and this program would run much faster because it's doing its work. Most of the work happens here, and there could be an arbitrary number of these MPLS headers, but they're happening 64 bits at a time instead of 32 bits. Okay, so what we'd like to do is to show that these two programs somehow are the same, that they do the same thing. And that's what this leapfrog system is going to do. Okay, so what we're going to do involves sort of work at sort of multiple levels here. So first, we're going to define what you might call a DSL. We call this P4 automata, or P4A. This is an abstraction of the real parsers that you have in the real P4 language, but it very closely mirrors the constructs and types and structures of that domain. And so we'll start out by just sort of defining this abstraction, its syntax, its semantics, what we mean by equivalence. Then we want to solve this core problem of determining, when are two parsers the same. And I'll take you through some of the tricks we did to make that possible, and in particular to make it fast. And then I'll probably be short on time, but at the very end I'll tell you about how we embedded all this in the Coq proof assistant, giving us what we call a push-button tool. So you can give it sort of two programs that implement parsers, and you can just ask Coq to prove them equivalent or not. And if they are equivalent, you get back a yes, and in fact a proof certificate that can be checked in Coq's underlying logic saying, yes, these two programs do the same thing. Okay, so let's see. So let me tell you a little bit more about this language. So these are the kind of pictures I've been drawing. They look like automata, but they've got these statements in the bodies. Formally, we can write this down as this little language. I don't want to spend a lot of time going through this, but let me just highlight a few things. So we've got, at the top, we've got some definitions of things like the names of headers. That's what we're going to sort of, the ultimate effect of these parsers is to populate a sort of store or memory with a bunch of parsed headers. We've got natural numbers, we've got bit vectors. These are the numeric values that our programs work with. We've got expressions. This is a very simple expression language, but these are expressions over these numbers and bit vectors. And they include things like referring to already parsed headers, literals, taking slices, so you can sort of grab bits 17 to 45 of something you've already parsed, and then concatenation. So this is these are the things that we'll put, for example, on transitions will be made up of expressions. And then we have patterns. So patterns, you can either match some bits or you can ignore bits. And then we have states. So states are, we'll have some finite set of state names plus two special states, accept and reject. And then, let me see. Let me jump down here. So each state will have a little program associated with it. And working backwards, we have the name of the state, we have its operations, which are either this extract operation that pulls bits out of the packet and populates some header. We have assignment, which we can use to imperatively update things like our parsed headers or other variables. And then we have sequential composition. So in general, a parse state will sort of do a bunch of these operations, and then it takes a transition. And a transition can either directly just jump to another state, like accept, or it can have a conditional, which we write with select, but you can think of this as just like a switch statement. So, match this list of expressions against a bunch of cases, where each case is a pattern with either some bits that we match, or you can also have don't care values if you care to ignore some of the bits, and then go to some state. Okay, so this is just sort of a little language that captures what we draw pictorially like this. The main thing I want you to pick up is that we have this little language here for the body of for the bodies of the states, and then we have these transitions, which are basically just a big n-way conditional on some values that we parsed so far. Okay, so just to show this in pictures, just to connect what we've seen, so we have these states, we have the accept state and the reject state. Apologies if anyone is colorblind. I realize these colors are probably not ideal for that. We'll draw the accept state with double rings as usual to try to distinguish it from the reject state. And then what we're calling the operation is the sequence of statements inside the state, and the transitions we just draw as all these tests going to other states. Okay, so the first challenge is, these P4 automata, they're really like what used to be called in the 60s flowchart programs. And we would like to decide equivalence for these things. And so to do that, we're going to build an alternate semantics that doesn't treat them as imperative programs, but instead treats them as automata. Sorry, that should be, meanwhile, a finite automata, not a finite. So what is a finite automaton? Well, a finite automaton is defined in terms of typically a finite set of states, but you could also think that there's a finite set of configurations. These are the state and any other information like, for example, the string you're matching and so on. It has a finite set of final configurations, and it has a transition function that goes from configurations to configurations, having matched some piece of the input. So how are we going to do this for our little P4A language? Well, and I'll say this took some care to come up with. This was one of Tobias's big contributions, was finding a really clean and elegant way to model these, if you like, flowchart programs just as ordinary automata. So we're going to pick our configurations to be a tuple where we have the state that we're in, we have the store, that's the memory of parsed headers that we've collected up so far, and importantly, this is actually also finite, so we can sort of enumerate all the possible locations in the memory that we might want to populate with this parser. And then, the sort of thing that's not obvious is, we're going to have a buffer, which we write as W. And so the buffer is just a sequence of bits, and we're always going to maintain the property that the length of the buffer will be less than the number of bits we would need to execute the operations in the body of the automaton. What do I mean by that? Well, the body of the automaton has, remember, it has assignments, it's got sequential composition, and it has these extract statements. An extract grabs bits out of the packet and puts it into some storage. So you can think of that as inducing some sort of length, how many bits do I need to kind of execute this state's effects? So we're going to call that sort of absolute value of op of q. And so the buffer will build up from nothing until we get to enough that we can actually execute the body. Okay. And the final configurations of this particular automaton are going to be triples where the buffer is empty and the state is accept. Okay, so this is our condition for when we accept a packet is if we can step through this machine, taking transitions, and we get to a configuration that looks like this, then we've successfully parsed and we accept the string. Okay, so those are the configurations and the final configurations. So to finish interpreting these things as automata, I just have to tell you how to define the transitions. And so we're going to define a total function, delta, as usual, that takes a configuration, one bit, and gives us another configuration. So the first thing I'll do is I'll just handle the accept and reject states. So if you're ever in an accept state and you parse anything, and you match any other bit, then you go to reject. And likewise, if you're ever in reject and you consume one more bit, you stay in reject. This is not so essential. This is sort of just a convention, but it kind of keeps some of the underlying math cleaner if we just treat the accept and reject states as having transitions that all go to reject. Okay, the interesting case is for non-accept and reject states. So if we're in an ordinary state Q, and we know that if we take one more bit from the input, that will still leave us with not enough to execute the operation in this state. Then we do that. We consume one more bit. Here I've depicted it as a 1, but there's another case where it's a 0. And then we go to the same configuration where now the buffer has one more bit. Okay, so this thing sort of eats one bit at a time from the input. The other case is where if we eat one more bit from the input, we exactly have the right number of bits to do the operation. And so here, we have to update our store. So we do the operation on the buffered bits. That gives us a new store S prime. And then we also compute what state do we transition to. So given the state we're in, the store, we need the store because we might have to interpret these expressions that we have on the transitions. Then we compute the next state, which is Q prime. And then we step to Q prime, where the store has been updated and our buffer has been emptied again. Okay, so nothing too complex here, but I want to stress there's a lot of care in this setup to let us interpret these seemingly imperative programs just as finite automata. Okay, so now that we have the syntax and semantics of our language, let me actually just ask, what's my time? I didn't take a note of what I
10,
said.
15.
Okay, great.
2 more minutes.
Okay, so now we want to sort of solve the problem that I said we set out to solve, which is to decide when two parsers are equivalent. And for the sake of this talk, I'm going to stick to what you might call language equivalence, which is we're going to consider two parsers to be equivalent if they consume exactly the same bits, meaning they end up in the accept state with empty buffer for the same, for the same inputs, and they reject strings in the same way as well. This is a little bit different than sort of what you might call full program equivalence, because we have these effects. We have a store that's being produced as we go along. I'll refer you to the paper, or you can ask me in the coffee break. It's not too hard to extend what I'm going to show you to handle notions of that approximate program equivalence. So in particular, we can prove things like these things actually end up in the same store. Or you may have noticed in the unrolling loop example I showed you, the names of the parsed headers were not the same, but there's some obvious relation between them. So we can capture that kind of reasoning as well. So there's more we can do, but I'm just going to focus on this simpler notion of language equivalence to keep things simple. Okay. So the game is we have two automata representing two programs, and then we want to decide if they accept the same set of strings. So in general, the way that you do this for systems that are like automata is you find what's called a bisimulation, which is a fancy word. What it means is, so we have these two automata, and they both have some state spaces, and they both have transitions. And we want there to be some relation that sort of says which states are the same. So the relation will be on the states, and maybe the start states are related by this relation. Maybe there's some other states that are related. And this relation captures what it means for the states to sort of do the same thing. It's called a bisimulation because you sort of want it to work symmetrically. I'll defer again, if you want to hear more about that, I'm happy to talk about it. But essentially, we're trying to find some way to relate the state spaces of these automata. So formally, we want to have a relation which is a subset of the sort of Cartesian product of these. I said state space, but I really mean the configurations. And we want it to be closed under our step function. Right, so we wouldn't be too happy if we had a relation that maybe related to start states, but then as soon as you do anything, you end up in unrelated states. Right, that would not really capture any reasonable notion of equivalence. So we want it to be closed. You can take any number of steps and you still stay in the relation. And we want it to only relate final configs to other final configs. So in particular, the accepting states should only be related to other accepting states with empty buffer. Okay, and if we find such an R, we find a relation on the configs, and it relates to these two configs, then starting from those configurations, you're guaranteed to have language equivalence. And in particular, if we start from the two start states, then the two parsers are recognized language equivalent formal languages. And I'm going to draw this just for convenience. You can think of this as working really on two independent automata. A really common thing to do is actually to compute the product automaton, where the configurations of the product automaton are just pairs of configurations of the individual automata, and you take transitions in the obvious way. Take a transition in one machine and the other machine, and that's the state that you step to in the product automaton. So I'll draw pictures like this. Okay, so how could we find, what's an algorithm we could use to find bisimulation? You've probably learned algorithms, again, in your undergrad theory of computation course, but a really simple way is we could sort of start, the intuition here may be slightly off, but start from below. So start from sort of the smallest relation that we know we must have, and then sort of expand it until we've satisfied all the requirements of a bisimulation, or if we fail, then there must not be a bisimulation. So that's the intuition here. We start with, in the product automaton, with the two start states, and then we just keep adding stuff to R as long as we have to. So, if we sort of take any state take any pair of states that's in R, if they can transition to two other states and those states aren't in R, and if those two states you can step to agree on being in the final set, then put them in. If not, then of course you fail. Okay, so this kind of just graphically works like this. We kind of build it out until we have an R that captures all of the configurations reachable from the start configurations that behave the same. And this produces what you might call the least by simulation. It gives you the smallest relation that has the properties we want. So there's another way you can build by simulations, which you might consider as sort of from above. So the idea here is we're going to treat this space, this white space in the middle, as being sort of the by simulation that we're constructing. And instead of building it up from small things to bigger things, we're going to start with the biggest thing we could imagine, and then we're going to cut it down by removing pairs of configurations that don't satisfy our properties. So we'll start with this set. So we're going to take the final states of the first automaton and the complement of the final state, so everything that's not a final state in the second, union the opposite. So these are all the bad pairs, right? These are the pairs of states where one machine is final and the other automaton is not final. Drawn them here as a skull. And now, instead of searching forward for transitions, we're going to search backwards through our machine, and we're going to remove things that could transitively reach one of these bad state pairs, configuration pairs. So, maybe there's some state here that can go to these bad configurations. We'll remove that as well, and this one, and this one, and this one, and so on. And so now, so we do this again until we can't do it anymore, until we reach a fixed point. And whatever R we're left with here, shown here in white, which is the complement of this other set of bad things that we computed. If that thing has our two start configurations, we're happy because the two automata actually are equivalent, and there is a bisimulation captured by this R here. Okay, so this is what you might call the above. And this is a good idea in general, but doing this literally for our automata is not going to work. And the reason is that our automata, they represent actually a massive space of configurations. For our trivial example that I used to motivate this, there's 2 to the 128th possible pairs of configurations. And if we do this with a concrete representation and a concrete sort of search through the space, that's just way too big to finish in a reasonable amount of time. So what can we do? Well, there's a couple of standard tricks you can do. One is to use symbolic techniques. So instead of sort of actually stepping through the concrete transitions that work a bit at a time, we can introduce some logical formulas that capture the regions that we're trying to represent here. And then instead of just taking one step backward, we can use a technique called weakest preconditions. This is the kind of thing you do in a program logic, where you have a postcondition and you're trying to figure out what precondition would be guaranteed to make that postcondition true. We can use that same trick here and work symbolically. So we start with the bad states as before, but now they're described as a formula instead of as a big set. And then we apply this symbolic idea from program logic to exclude other regions of the space, and all of these circles are represented as formulas. And then at the end, we just check if the space represented by our initial configurations is not in the space covered by the pink circles. Okay, so this is pretty good. This helps. There's another limitation, though, which is the way that we defined our automata with this very careful one bit at a time parsing means if you do this, you end up applying many, many, many weakest precondition steps through all these states. So this is sort of our machine. This is showing our machine running this command, right? If we extract UDP, we sit and parse 64 bits, and then we finally do the real transition to the accept state. And so if you did this in an implementation, you would end up running this weakest precondition operation through 63 very trivial steps until you get to finally the one that sort of triggers the real transition to accept. So it'd be really nice if we could eliminate these sort of small and very mechanical, very simple steps. Right, that's the actual state transition happens somewhere way back here. And so this is another trick that we use. It also builds on some symbolic representation, and it's where the name leapfrog comes from, because we say that it helps us sort of leap over these sort of administrative or very mechanical transitions. So the idea here is, here's a formula that we're going to write down that describes the relationship between these two states, and we're going to add some numeric constraints on how much is in the buffer. So initially it's 0, because remember our final configurations say the buffer's empty. And the arrows here just mean left automaton and right automaton. They don't stand for less than. That might be confusing you. These are just left and right. So, the automata that I defined for you, ultimately we want to relate these two states, right? Where we're in Q2 over here, and we've buffered 63 bits, and over here maybe we've buffered, let's say 223 bits coming from some parser here that extracts everything in one. So sorry, this is not the same example as before, to be clear. This is just, here's two states we could parse sort of one then two, and over here we do all the bits at once. And we want to relate these two states under sort of different conditions about how much has been buffered. But if we do this sort of naively, we end up with many, many, many iterations doing these administrative steps. And then finally, we get to the one where we can take a leap. So the idea with leaps is that we can essentially do a static analysis to compute how big the buffers are going to have to be, and then build just one rule that leaps over this whole operation in a state in one step. And for anyone who's done some more advanced automata theory, this is what's known as an up-to technique in the literature. There's a beautiful paper by Filippo Bonchi and Damian Puss that sort of describes how these work. And roughly the idea is, because we know something about the structure of our domain, we can construct a small relation, which is not itself a bisimulation, but we know that it can be systematically extended to a full bisimulation. And we prove that either in calc or pencil and paper once and for all. And then we can get by with just searching for this smaller relation. And the fact that we can search for a smaller relation really speeds things up. Okay, so now, instead of taking all these hundreds of steps, we can just do this with leaps in just 3 steps. So just 3 weakest preconditions computing these pairs of states, which makes us happy. I'm a little short on time, so I'm going to skip over this. You can do some further optimizations with some static analysis. Just to show you that this stuff really works, in our paper we took a parser that came from a paper by some networking folks who were thinking about these programmable parsers. And we were able to take some of their benchmarks. So here's the kind of programmer-written parser that you might have in a data center, for a data center router. And here's the version that the compiler would like to produce after it's done this kind of unrolling and optimization. And we were able, so we ran their parser, which produces this thing, and then we built a back translation into P4 automata, and then we were able to actually prove that these two things are the same. So this gave us some confidence that this technique can really apply to real parsers. I just want to show you what this looks like in calc. So this is, I mentioned that we have a push button tool that can, you give it 2 parsers, and you ask it to prove them equivalent. Here's the proof that you do. And it's, as you see, it's fully automated. So once you've invoked this tactic with the right arguments, you just get back a proof. What probably went too fast is, behind the scenes, this is doing a bunch of work with an SMT solver. So equivalence here is decidable, but a lot of the steps of reasoning you need to do involve very fiddly, low-level reasoning about essentially first-order formulas over these bit vectors and such. So I know I'm short on time, so I'll just sort of flash this up and maybe explain it if people want later. Essentially, we built a plugin that goes and finds a bisimulation, but whenever it gets to a condition that involves reasoning about some decidable first-order logic property about maybe bit strings, instead of going and proving that in calc, we just pass it off to a SMT solver like Z3. Z3 tells us whether that formula is valid, and then we get back the answer, and we put that into our development. And there's some cool details about how you actually engineer this kind of system, but the upshot is you do get this push-button calc tactic, and you get a proof script that tells you the two parsers are equivalent, and that proof script relies on these first order properties that were proved with the SNP solver. So I want to be sort of clear that you get a proof script that tells you that the parsers are equal, but it's contingent on the correctness of these first order properties that were farmed out to the SNP solver. Right, so essentially we're not reconstructing proofs of first order formulas. There's other work out of Stanford and MIT and other places doing that, but modulo that sort of assumption, you do get this very strong notion of assurance. The other sort of caveat that I want to give about this line of work is, we invented this DSL, P4A, and it's really an idealization of P4's real parser language. And I'll just mention we had some work at CPP this year that's working to close this gap, so building an actual compiler from the real P4 parsers into P4 automata and proving that those things are equivalent. Okay, so I'm kind of going to end a little bit abruptly, but to bring it back to our top level sort of philosophical point, I think there's sort of this common perception that DSLs are somehow simple or restricted or not interesting. And I have the complete opposite view. I've actually spent my whole career in PL research working on DSLs, and I just find them this amazing fountain of sort of sources of cool problems. You basically go to practitioners in other domains, you ask them, how can PLs help you, and they'll always have problems that they can give you. So I found this a really fruitful way to find cool problems. We've talked a lot about parsing. Parsing is one of these classic problems that you sort of think is solved, but it continues to be a very important domain, and there's lots of cool stuff you can do, often building on beautiful structures like grammars or automata or algebraic presentations and so on. And the other message I want to have is that, when you go into domain and do this work, it doesn't mean that you're going to be doing sort of hacky work or work that's shallow or something like that. You can use some high-powered machinery, and you can even contribute to some of that high-powered machinery. Things like, bisimulations and mechanized proofs in Coq and so on. So, there's some art to applying these things well. You have to set things up so that you can do that, and that requires the kind of, aesthetics that PL people have. We tend to set things up very cleanly and formally, but when you do things right, you can actually build a bridge and apply these kind of power tools to these grubby practical problems. Okay. I'll just leave you with some pointers to the Leapfrog work if you want, and I want to again acknowledge both Ryan and Tobias, who were the junior people who really drove this work, and if you thought this was cool, all the cool ideas came from the two of them. And I think I'll stop there.
Great. Let's thank Nate. As he mentioned, I think he'd be happy to answer any questions that you have kind of during coffee break, which is starting around now. So I'll let that happen on a one-on-one basis. A couple pieces of business before I let you go get caffeinated. One, if you haven't done the attendance form for this session, please do that. QR codes are on the chairs as you walk out. And then we'll come back together and start with a talk and then a panel. And one note is if you'd like to submit questions for the panel via text rather than via voice, you can do that in the attendance form for the next session. So thank you all, and I'll see you in about half an hour.